What's up, guys? So it's me, Sir Ernest, and today we are going to talk about conservation of energy in Lagrangian dynamics. So previously, or in our previous video, we've talked about conservation of momentum in through the Lagrangian of your object. Now, today we're going to look into another conservation law, and we're going to look into conservation of energy. Now, for example, if we have a closed system, okay, consisting of several particles, or maybe one particle, and this closed system, okay, is said to have, for example, a kinetic energy that is a function of velocity, qi dots. And this closed system is also described by its potential energy, which can be a function of both position and your velocity. Okay, so this tells us that the Lagrangian is only an explicit function of position and velocity. Although we know for a fact that the position and velocity of your system are functions of time. But the Lagrangian itself is not an explicit function of time. So therefore, this leads us to the first statement wherein the partial derivative of the Lagrangian with respect to time is equal to 0, because the Lagrangian is only an implicit function in time. So therefore, the total derivative of the Lagrangian with respect to time, which follows chain rule, because remember that the Lagrangian is an explicit function of position and velocity, but an implicit function of time. So this means that Lagrangian is an implicit function of time. Position and velocity are functions of time, but the Lagrangian is not an explicit function of time. So therefore, the total derivative with respect to time of the Lagrangian can now be rewritten as follows. This is partial derivative of L with respect to Q I times the total derivative of Qi with respect to time. And then we have to sum this for all i's, plus sum for all i's, where i's are your specific coordinate that you're going to use. So this is the sum of all of i's, partial derivative of L with respect to Q I dot times the total derivative of Qi dot with respect to time. Of course, we can also do this as follows. But as I mentioned earlier, because the Lagrangian is not an explicit function of time, this is 0. Okay, so this is Qi dot and then this derivative of qi dot with respect to time. So we know for a fact that the derivative of the Lagrangian with respect to position is actually the time derivative of the Lagrangian with respect to velocity. This is from the Euler-Lagrange equation. This is actually equal to this times qi dot. Because this sum and this sum are all in I, so therefore we can take the sum, the summation of the sum. So in other words, we can take this operation out like this, and we just copy this one. So this is plus derivative of L with respect to Q I dot times derivative of Q I dot with respect to time. So you will notice that these two terms is actually a result of a product rule. And that product is actually the product of this term and this term. Right? Think about that. Okay? So these two terms is actually a product of the total derivative with respect to time of qi dot and the partial derivative of L with respect to qi dot. And this is happening when you sum it for all i's. I hope this clear. I hope this is clear. Now, because this is total derivative of L with respect to time, we can rearrange this as follows, wherein the total derivative of the Lagrangian minus the sum of qi dot times the derivative of L with respect to qi dot. And this is equal to 0. So again, we are now presented with a derivative with respect to time of a quantity. And that quantity is this one. So we call this quantity the Hamiltonian. And it is usually represented by H. The Hamiltonian of the system is equal to H, and this is equal to the sum for all I of qi dot times pi minus Lagrangian, wherein your pi is equal to the partial derivative of L with respect to qi. Okay? So this is the Hamiltonian of a system. Now, if for example, let's say that we have a sorry about that. So let's say the potential energy of your system is only a function of your coordinate. Sorry about that. Should be coordinate. Okay. So that means from our Lagrangian, the partial derivative of the Lagrangian with respect to q I dots is equal to partial derivative of t minus u with respect to q I dot. Okay, now from here we know that this will allows us to state that the Lagrangian is a function of q I and q I dot, but but this dependence on the velocity of the Lagrangian is only because the kinetic energy of your system of particle or system or particle is dependent on velocity. So if we're going to do that, this is equal to partial derivative of L respect to q I dot minus partial derivative of u with respect to q I dot, which is 0, which is equal to partial derivative of t with respect to qi dot. So therefore, the Hamiltonian of the system is H equals sum of q I dot times the derivative of L with respect to q I dot, which is equal to derivative of t with respect to qi minus the Lagrangian, which is t minus u. This is for all i's. Now if we're going to recall this one, the partial derivative of the kinetic energy with respect to qi dot is partial derivative with respect to qi dot times 1/2 m times qi dot squared, which is equal to m qi dot. Okay, so this tells us that this is equal to sum of qi dot times m qi dot minus t minus u. Combining this, we have m qi dot squared minus t minus u over I. Now, if we're going to multiply this by 1 equals 2 over 2, this term becomes 2 times sum for all i's of 1/2 m qi dot squared minus t minus u. And what is this? This is your total kinetic energy of the system, which is equal to t. So this is equal to, the Hamiltonian is equal to 2t minus t minus u, so this is plus u, which tells us that the Hamiltonian is equal to t plus u. And what is t minus u? T minus u is the total energy of the system. And we know that this is a constant. Okay? So in this case, the Hamiltonian of the system is equal to the total energy of the system, and that is a constant. So that's your conservation of energy. And this happened because of two conditions. Number one is the kinetic energy of the system is a homogeneous function. It's a homogeneous quadratic function in the qi dots. So this is a quadratic function in the qi dots. Also, the potential energy is only a function of position. So that means your kinetic energy must be velocity independent. And if those two conditions are met, therefore, the Hamiltonian of the system is equal to the total energy of the system. Okay? So please beware that there are books that all automatically say that the Hamiltonian is equal to the total energy. But that's not always the case because that relationship between the Hamiltonian and the total kinetic energy is this only if those two conditions are met. Okay? So this ends our presentation today. I hope you learned something today. And thank you for watching. I'll see you again in the next video. Bye-bye.